down. All right. So any questions over 3, 4, 4, 1? 4 is not that evil, but yeah. Oh yeah, so this one gives you a list of numbers, and it says find the percentile. So it's different from find like P70. They're asking you to find what's the percentile of a certain data point. So let's see, they give you this list of data. This is number 17, page 128. And they say 54, what's the percentile for a data value of 54? They're not asking you to find P54. That's not what this is saying. Otherwise, they would say P54. It's crazy how obvious they try to make it what they're asking for. This one's asking you, that 54 in that list of data, what percentile is it? So if it was right in the middle, what percentile would that be? 50th. I love it. So really all you have to do is count how far in does it take to get to that data point and see what percentage of all the data that represents to get there. Does that make sense? So that's kind of a backwards question from this. This is find a data value that is the 54th percentile. This says 54, that data value, what percentile does that represent? Is that cool? I think they do an example of that somewhere in this section. Is that all right? Yeah. Does that sound familiar? All right. I don't blame you, because it suddenly just changes gears, right? Yeah. You're going forward, and all of a sudden you're in reverse. Yeah. That's what that one means. It's not asking you for P54, it's asking you for the reverse. What percentile would that represent? I like it. Anything else from homework? Okay. So let me ask you this. I'm going to try something out. I couldn't find my cards. I have like a deck of cards in my office. I wouldn't really do too much with them anyway. We're not going to sit down and only break into several tables of No Limits Texas Hold'em or something. Hey, look at you with the deck of cards. Come here. All right. So have we ever met before? Yes, we have. That's right. Looks like it's roughly shuffled. So let me ask you this. One thing I like to do. Well, actually, let me do something else here first. I think you guys are all cool with cards. Is that right? You're all decent with cards? Anybody not really know cards too well? You don't have to know it well enough, like one-eyed jacks. I'm not getting down to that specificity. It's how many kings are in a deck of cards, stuff like that. Cool? Okay, I don't want to bend your cards. That would suck. So if I were to pick a card at random, it's my favorite card. What's the probability? Somebody give me a guess as to what this is. Somebody raise their hand. All right, what is it? 7. Of what? Hearts. Okay. So what's the probability that he's right?
1 out of 52.
Yeah, because it's very specific. He said 7 of hearts. There's only 1 7 of hearts out of the entire deck. Now, what if I backed off a bit and I gave him a break and I said, "What? Just for a set." So the probability of a 7 of hearts is 1 out of 52. 1 of those cards out of 52 total. Now, what if I said, "I'm just going to take your 7"? What's the probability he's right then? Yeah, 4 out of 52. Now, why is that less than that? It's almost a silly question. Why is that a lower probability than this? More specific. I love it. So this is really a list of properties the card has to have. Not only does the card have to have a 7 on it, it also has to have a hearts on it, right? So it has to meet both. So this would be a situation that would be, and we'll come back to that later. This would be a much more forgiving situation. 4 times higher. The probability you're right would be 4 times higher if I just said saying a 7 is good enough. You guys with me? And that real quick, a friend of mine, she said something about, she wanted to have a baby. This is a long time ago. She was getting to her, she was like 32, and she was freaking out. Because she'd heard the older you get, your chances of the baby having this and this and this problem are tripled and all this kind of crap. And if you look at it, the original chances your kid would have that problem would be 0.001%. Now, can you tell me what the hell does that mean? What does 0.001% chance mean? I love it, because if you write this as a fraction, first as a decimal would be back twice. So you have to have 0, 0, 0, 0, 1. And then that's tenths, hundreds, thousands, 10,000. That's actually tenths, hundreds, thousands, 10,000s, 100,000s. 1 out of 100,000 chance. Which really means what? I mean, I kind of got into this a little bit last time, what probability really means. What the hell does that mean? I like it. So for any specific kid, if you just pick a kid at random, right? And the hospital is probably going to throw you out if you're just in there going, this one. That's probably, especially if you say it like that. But if you just pick a kid at random, it's a very, very, I'd put money on the kid not having this thing, right? I put a lot of money. I'm a teacher, but I feel pretty good about them odds. But what does it really mean then? It doesn't mean much for a specific kid. Because then my brother sort of becomes right. Either he's got it or he doesn't. That. Which is, that's exactly what my brother sounds like. But what does this really, really mean then? I think I said this really quickly last time. It's already been a long time ago. What does it really mean? If I took 100,000 babies, how many would I expect to find that have that condition? 1. So this probabilities in general do not mean much unless you do something a lot. It's actually really related to physics. We won't get into physics, right? But the probability if you flip a coin, what's the chances it's going to come up tails? 50-50 because we're assuming it's a fair coin, right? So both sides are equally likely. Cool. But if I flip it once, what does that 50% mean? Doesn't really mean shit. So I can look at it 2 ways to make it mean more than just shit. I can look at it. If I do that 100 times, I expect how many tails? 50. You with me? Which really translates to what? What do we really mean there? I expect to not see maybe how many tails?
51.
No, 51 I'd be cool with. I guess I mean to say, what would I not be cool with? What would tell me something freaky's going on? 100's a good way to go, an extreme. If I saw 100 tails, what is that good evidence of?
Tampering.
Some kind of tampering. It's the coin they used in the Super Bowl a few years ago. No. It's something's been done to that coin to make that happen. Now, it's not impossible that would just happen. But what's more likely is that somebody tampered with the coin. Are you guys kind of with me? So there's the situation about we have to understand what probability really means, and then we have to understand how do you use it appropriately, right? The human brain is not hardwired to do either of those things, which really sucks because we just got to keep reminding ourselves, okay, that's what it really means. You know, and people misuse probability all the damn time. It drives me crazy, right? If you're 95% certain it's going to rain, is it going to rain? No. If you go in to a casino and you play, you like pull the lever in three machines, is it impossible for you to win on all 3 machines? Win the big money, win $1 billion on each machine. Is that impossible? No, but a lot of people said it was. I think it was like Wayne Newton or something stupid in the homework problem. I don't know if you guys remember that from a while back. It said, tell me if this situation's impossible. David Letterman was speeding or something. You guys remember that? Or am I completely, is that a dream I had? I don't know. No. It sounds like a dream I had. Very strange.
I don't remember the slot machine though, but I remember this.
There was something about you win the jackpot on 3 different machines on the same day, and a lot of people said, no, that's impossible. Of course that's not impossible. But our brain automatically says, that's not going to happen because it's so unlikely. I'm thinking it's impossible, right? So, let me see. I'm trying to figure out which way to go from there. Oh, I still got my card there. So that's what this means. And really what's interesting about probability, and I don't know if anyone really wants to know what the card is, you're going to have to wait. There's 3 types of probability. And we've already seen one of them before we got into this chapter. And that was where if I talk to so one type, talk to 50 people, find 11 that don't want Jay Leno to leave? Yeah, I know. It'd at least be 12 if Jay Leno got into the thing himself. But I'm okay with Jay Leno going, by the way. I don't care. I don't watch the damn show. I might now. Talk to 50 people, find 11 that don't want Jay Leno to leave. So this sounds a lot like when we did a histogram, right? We could find 11 people that don't want to leave, 14 people in another group, and I can make them a What's the relative frequency related to this? Yeah, I like it. 11 out of 50, 22%. So besides just calling it relative frequency, you can also call this the probability. This would be what's called an empirical probability. The book calls it, every book I use uses a different name. Oh, they call it the relative frequency approach, but it's really called empirical probability. Empirical probability is based on observations. Strictly based on observations, right? But if I took a card and I just threw it out there somewhere, just threw it, what's the chance it lands up on the king? What's the chance it shows the king? And what's the chance it shows me the blue background? 50-50. Did I actually throw any cards? Did I throw anything? No. Now, in this situation, now I know I didn't talk to 50 people, but let's all pretend. If I did go talk to 50 people, and I did find that 11 want Jay Leno to leave, that's empirical probability. If I just theorize what's going to happen, I think they call this the classical approach. Incredibly enough, I call it the theoretical probability. This is when you say something like the probability of a head is 1/2. Did you actually flip a coin? In fact, to get a feel for what the probability of a head would be, what would you have to do? Would you flip a coin once? If you flip a coin once and you get a tail, you'd say it's a 100% chance of a tail because it's 1 out of 1. So you'd have to flip it many times. I love it. And that's actually the connection between these two. And this is almost too intuitive, but I love the name anyway. The connection between these two probabilities. This is the one that we do based on observations. I look and I see how many people in here have blonde hair. Then I'll know the probability that I pick somebody with blonde hair at random just by observing. I see how many people have blonde hair divided by everybody. That's empirical. This is theoretical. I don't do a damn thing. I just think about how many coins are, how many sides to a die is there, and so forth. I just set up the probabilities that way. Are you guys kind of with me? The connection between these two is called the law of large numbers. You got to love that name. Well, you don't have to, but it's not one that I made up. It sounds like one that I made up, but I can't take credit for it, right? So what that says is these probabilities will approach these probabilities if you do this a lot. If I actually throw that card out a lot, I should start to see that if I threw it 20 times, I should start to see 10, 9, 8, 11, somewhere around half of it should be on one side or the other. Are you guys kind of with me? Okay, maybe. Okay, so that's the connection. There is one other kind of probability. Subjective probability. If I asked you what's the chances you're going to pass the next test, you would probably give an answer based more on how you feel than on any mathematical calculation. Is that true? And of course, what's that word subjective mean? It means feelings. It means intuition. It doesn't mean objective would be calculations, using theory, using some kind of mathematical analysis. We're not going to use that one very much, obviously, because this is a math course. It's great. But subjective probability is just how we feel about something. What's the chance it's going to, what are the chances that you're going to, what's a good, well, weather predictions very often are sort of subjective. Because different weather people can look at the same data and come back with a different response. They can think about it a different way. But that's a little bit on the edge. We're going to focus on these two. We've already done a lot of this. I just didn't call it probability when we were doing it. And we're definitely getting into doing a lot of this, the theoretical probability. So coming back to this. Right? So what really freaked me out is that's a 7 of diamonds, so you're freaking me out in the back. I'm going to wear tin foil on my head. So you're doing the test, you're like, the answer to 3 is 4. So that's neat. I never had somebody come that close. Let me try. 5 of clubs. Shit, all right. So that was kind of cool. If I did this a slightly different way, if I did this picking a card thing a slightly different way, I want to get into some other stuff with probabilities. Has everybody got this here? Yeah. Before I do whatever the hell is these boxes all about, still thinking about a deck of cards. Normal deck of cards. Let's do a couple things real quick. Let's probably pick a jack. Yeah, we're getting tired of that one, right? It's like, Jeff, any damn things can be 4 if it's 2, right? All right. I understand. That's what you want to say, but you didn't feel like you should say it because of the teacher. Well, let's probably pick red jack. I love it. There's only 2 red jacks out of 52 cards, which reduces to, look at me looking ahead. I like it. 1 out of 26. Because the deck itself, how many different colors in the deck? 2. And they're equally divided. So there's 26 black cards, 26 red cards. Cool. So 1 out of those 26 red cards is a jack. That's the way to interpret that reducing.
The joker doesn't include 3?
No jokers. Yeah, we take the jokers out. I have no idea. I don't think there's jokers in there, but there could be. And this is that idea of, another way to say this would be red and jack. Because they have to be both. So there's that hidden and. Very often in mathematics, we don't see the and. In English, it's implied. If I said, did you see that red car? It's a car and it's red. I don't have to say that. Did you see that thing that was a car and... No, screw it. But in statistics, if I can rewrite it to have that and there, it'll help us out. Later, we're going to talk about how to do more complicated and problems versus what we're about to do right now, the or problem. Jack or, what you got, Jeff? 8. It's a jack or an 8.
8 out of 52.
I love it, because what's the idea of probability? The most basic idea of probability, which actually never changes, is on the top you put the total number of things that match what you want. I want a jack or an 8. So how many things match what I want? 8. 8 things match what I want. I'll take either one. So or is more inclusive. It says you could be this or that or that. So when you're looking at you're looking for a job. Do you get this often when you, well, or you're trying to get a scholarship? This might be more immediately pressing. And I used to do this in the financial aid office. They had this giant book, and nowadays, of course, that book is probably online. But way back in the dark ages, we had the scroll of scholarships, and you start reading through it and say, okay, cool, I'll get $5,000. You have to be a math major. Cool. And you have to have at least this GPA. Cool. And you have to be a woman. Okay, shit. What's the next one? I'm like, put that first. What the hell? Are you guys kind of, I don't know if you've ever had an experience like that. Are you looking for a job? You have to have experience with this. Cool, I got that. You have to have 7 years experience in the field. I'm screwed, right? So the and is more restrictive. Less and less people would meet the requirements to get the job, to get the scholarship, and reduces the probability of that. Or increases it. You never see or with scholarships or jobs. It sucks. Well, sometimes jobs. You have to know Microsoft Word really well, or You have to do PowerPoint really well. I don't know. They just want somebody to know something. You kind of with me? And then more people would actually, if you don't know a word, but you do know PowerPoint, you're good. So Jack or 8 is definitely going to be higher than Jack alone because I've got more chances to meet what I want. So it's actually twice as much. What are you doing? You want to go there? You go down there. And of course, the 2 out of 13, if I reduce it, means 2 cards for every suit matches what I'm looking for. Is that cool? All right. Now, or is not as nice as it seems. What did we really do with the Jacks and the 8s? Mathematically, we just added them, right? 4 Jacks plus 4 8s. And I got 8 cards. So there must be something weird about this next one. Well, probably it's a Jack or a club. How many clubs are there? 13. Yeah, be careful. Every suit has 13 cards. So it's 13 clubs plus how many Jacks? 4.
17.
Now if I do this, that's wrong.
It's 18.
Careful.
Because one of the jacks already has clubs.
11. So when you count the clubs, when you do 13 clubs and you have them and you lay them down on the table and you go to reach for your Jacks, do you have 4 Jacks you can hold on to? If you only have 1 deck of cards, don't go cheating. You only have how many Jacks? 3. Because what happened to that other Jack? It's already in those 13. So if I do this, I have done what, essentially? 1 card I've counted twice. Thank you. So here, if I just subtract 1. And what does that 1 really mean? It's that 1 card that I did twice. How we doing? I like that. You guys are like, I understand what you just said. I don't know what the hell it means for me. What am I going to have to do? I got all that from the look. So, let me follow this up real quick. Or then, now why didn't we have that problem here? There was another or problem. I didn't have that problem. I didn't have to subtract anything. Of course, why not? Yeah, there's no 8 that's a Jack, unless you got the right, you're like, I need another 8. Whoop. You know, it's an 8 there and it's a Jack there. No, I'm not playing cards with you. Right? So there's the Jack or it's an 8. It can't be both. So this would be minus 0 because there's no cards that are both. Here I had to subtract 1 because there's 1 card that is both. You with me? If I said, let's do one more of those. Probability ace or black. It's going to be an ace or it's going to be a black card. How many aces are there?
1, 2.
There's 4 aces. So you can be smart about it. I like the fact that some of you guys are being smart about it. How many black cards are there that I haven't already counted?
26.
There's 26 black cards.
Minus
24.
4.
There's 24 black cards I haven't counted yet. So you could either go 4 aces plus 26 black cards minus 2 aces that are black. You with me? The ace of clubs, the ace of spades. Right? You can subtract those out. Or you can just be smart in the first place. You can go 4 plus 24. Or like some of you guys were trying to tell 2 plus 26. Either way you do it, you're going to get 28 out of 52. Right, which reduces down to 7 out of 13. Cool. How are we doing so far? So I'm trying to get you to really understand what and or mean in a stats class. Because in English, and doesn't always mean that. Right? If I said you and you, come with me, you're both going to go. You might think it's addition. Like you added these guys together. But and really means the person that goes with me must be at least 5 feet tall and know how to capture a badger and, whatever. So there's fewer people are going to be able to go with me. That's mathematically what the and is all about. Yeah. Have I know I have a deck of cards, but have I picked several cards and counted how many, jacks I got? That would be empirical if I did that, but I didn't do that. This is all theoretical. This is theoretical. Why is it theoretical? I haven't actually taken any cards out. It's purely based on what might happen. There are 4 things that would agree with what I want out of 52 total things that might happen. That's theoretical. If I actually sat down and did something very exciting for all of us and just picked cards, okay, that's a 6. Not a jack yet. You put it back. Okay, that's a queen. Got close. That would be, okay, that was horrible already. But I mean, if I did that, and I picked like 50 cards, and I saw 2 jacks, if I picked 50 cards, and I saw 2 jacks, what's the empirical probability of a jack? Equals to what? 2/50, which is 4%. Is that cool? You guys get with me? And of course, empirically, almost anything can happen. Right? I mean, I could pick, especially if I don't know if you guys noticed, but when I pick the card, I put it back in. And I have to be careful about it, because if I pick a card and don't put it back in, I'm changing probabilities as I'm going. So I always want to put that card back in as I go. But I could pick 1,000 cards like that and never get a jack. That's possible. So I might think the actual probability is 0. Yeah.
Although if you do put that card back, do you have to put it back, where would you have to put it back at?
Doesn't matter. As long as it was random to begin with, you actually want to put it back in a random spot.
Okay.
Yep. So there's a chance you'd repick it. But that's actually being the most random you can be. Yeah.
Just making sure you just don't put it on the bottom.
Yeah, don't like put it somewhere you're not going to pick from. Okay. Oh, let's see. Oh, so look at the formula for this. If I have probability of A or B. And as we go, I'm going to kind of do my definitions. I didn't want to throw all the definitions at you at first. We had chapter 1 for that. A and B, they're called events. And events are collections of possible outcomes. Outcomes are exactly what it sounds like. Outcomes are all the things that could likely happen. I mean, not likely. All the things that could happen, period. So the outcomes, all things that could happen. So A and B are events. So ace would be an event. I pick an ace. That's an event. Not an event as in come watch me pick an ace. It's just a thing that happened. So what would this formula really be? Maybe. And look mathematically up here. If I break this up, 4 out of 52 plus 26 out of 52 minus 2 out of 52, can you identify each part generally? What was this part? The probability of the first dude, right? So the probability of the first dude plus probability of the second dude, 11, minus, what was that? All the cards that were what? A and B. I love it. Say that magic word for me. A and B. So it's minus probability of A and B. So I don't know if you guys have ever seen Venn diagrams before. It's not some weird band. Have you seen Venn diagram in concert? It's here's A, here's B. So the most boring example would be like women and Democrats. You have some women that aren't Democrats, and you have some that are Democrats. So this middle part represents what? Yeah, this would be A and B. So if I think that probability of A or B is just take A, take everything in A, and add it to everything in B, visually you can see the problem, hopefully. I've added one section twice. So to make it correct, I have to subtract that section back off. So if I take A and add it to B, I have to subtract this section off, which you guys just told me was A and B. I like it. But when it was jacks and eights, what would the picture look like? If it was jacks and eights.
Circle upside down.
I like it. There'd be no overlap, at least not in my deck. right? Or your deck, hopefully. I don't know. I didn't look them all over. So that's why we didn't subtract anything off, because it's not because the formula really changed. It's just because this piece would be 0 for that. There are none that are both. I like it. Cool, cool, cool. Maybe. All right. So let me do this. I want to talk a little bit about probabilities and then about how to use them. So hopefully I didn't just show anybody this. Yes?
What does it say right underneath outcomes? All things.
That could happen. Yeah, all the things that could happen. In these boxes I have red and green little blocks. Oh, this is so exciting. So what I want you to do, I want somebody to pick one out for me. Pick out of this box. Let's do one box at a time. Pick one out. Red, cool. Pick one out. Red, okay, put it back in. Put it back in. Somebody pick something else. Red, okay, cool. Red. What do you guys think?
They're all red. I haven't seen it so far.
How did you? That's so awesome. I never know how this is going to turn out. All right, so up to the point that was so that I couldn't even design that better. We didn't meet beforehand. I didn't tell you where in the box that would be. Up until the point, I love what you said, and I love the way you said it. It was awesome. I get your point. Oh shit. That's not his point. Shit. But that's beautiful. Up to that point, I'd only seen red. I agreed with you. There'd only been red. So how could I expect that there's green in there too? This is the closest I can get you to an unknown situation somewhere out in the world. We want to see what's the probability somebody's going to be affected by this the runoff into a river. And we go out, we don't find anybody that was affected. Does that mean the probability of being affected was 0? No, because maybe if I just looked at one more house, just one more house, Aaron Brockovich. Go one more house. No. Aaron Brockovich? No. Okay. That you'll find the green cube. The person with a disease or whatever the hell it is. So this other box probably is somehow different or not. Maybe that's my point. Here. Green. Looks like your hypothesis might be right. Green. Not that one. Not good. So what do you think? I only had 3 people pick. So what do you think? Do you know?
All green.
There's a decent number in there.
Majority is green.
So there could be the majority is green. It could be that they're all green, right? You with me? So in reality, you'll never know. And that's, I hated that when I first saw that at a conference a while back. Somebody had a little bag of stuff, and I thought, and we went around and we had little pebbles in there. And somebody picked one, it was green, and somebody else picked one, it was green, somebody else picked one, it was green, and she said, what do you guys think? Well, it might be all green, but we're not sure. And she said, you'll never know. And we're like, because it's like, who cares really? But part of you is like, I need to know. But that, again, that's another thing about the real world. And of course, trying to teach the real world through little colored cubes is kind of silly, but in the real world, you're investigating a situation. You have no idea what the reality is. You have no idea how many people might have been affected or not, or whatever the situation is. The probabilities give you some idea, but they can never give you the whole idea. You can never know the truth. So statistics, to me, is the most honest branch of mathematics. It says, that's what it looks like. We're not sure. Do what you want to with that stuff. I don't know. So I love it. We can only, every time we give an answer in statistics, we always have to follow it up with, well, plus or minus 4 percentage points, because we're not really sure. And people hate statistics for that, but I'm like, that's freaking life. That's math exactly matching life. You'll never know for sure until the election actually happens, and then everybody's like, how the hell did that happen? The poll said this. Well, screw the polls. They can't know for sure. Okay. Don't know how you feel about that. I'm never going to tell you. There might have been all green. There might have been some red in there. I can't remember. Okay. So there's something from earlier in chapter 1 that I don't think I made a big deal about and nobody really ever asked in class. And it talked about statistical significance versus practical significance. Does that sound vaguely familiar? So to be statistically significant, that normally means that you've just done something that randomly would be really unlikely to do. So, for example, if I, let's see that, SAT scores are normally distributed. This is a fact because they're designed to be that way. And they have 100, not SAT scores, sorry, IQ scores. So they have a mean of 100 and a standard deviation, if I remember correctly, of 15. So if you know your IQ score, then you know kind of like where you fall. Mensa does 133 and up. If you have that kind of IQ, you can join their club and make Mensa cookies or whatever the hell they do. So I know it's normally distributed. I know the mean is 100. So if I claimed to have a way to improve your IQ score, like I don't know why I'm thinking about Lawnmower Man, if you ever saw that movie. I had some series of images you'd watch, and suddenly your IQ score would go up. Has anybody ever seen that movie? No? It's before your time, but they still have it on streaming. So, if I claim like I could take your IQ score and put it up here, and I have a group of people that do that. So I have a group of people that go through my little class, and their average afterwards is 140. So the average before was 100. So would you call that statistically significant evidence that my technique works? Now, of course, was one key thing I haven't said that you should realize is necessary. Did one person go through my class? I didn't say, right? So let's say, 60 people. What do you think? So if I claim that I can increase their IQ score by doing whatever this is, drinking the Kool-Aid that I make, or showing them images that somehow stimulate the brain, or chanting, something, and this happens, what do you think? Yes, sir. We do. We know exactly all we need to know about the population. Normally distributed, mean of 100, standard deviation of 15. Yeah. So this is where we're headed. This is the use of probability. If the likelihood that I just happen to pick a group of people that would end up here is very low, then what's more likely is my stuff worked. And that's very often how this happens. If random chance of it happening is very low, so I claim I could weight a quarter. I can weight it so that it comes up heads more often. What would be evidence to you that works? If I flipped 5 heads in a row, is that enough evidence? No. It's some evidence. You have to agree. It is definitely some evidence. You go, you might have something there. I don't know, do some more. So I do some more. The next 20 I do, it's all heads. How do you feel now? You're like, that's pretty damn good. It's not 100% evidence, and it never, I don't care if I do it 1 billion times. You can never say with 100% certainty. But if I did it 1 billion times and they all came up heads, you go, that's damn certain enough for human. Freaking hell, right? That would be plenty of evidence for us. But exactly where did it start being enough evidence? Was it 7? Was it 12? Was it 38? Was it 520? That's something we're going to talk about more later. But that's one example of how probability can be used. If the probability of something happening is so small, otherwise, by itself, just happening, then it might be evidence that, no, it didn't just happen, it actually is because of what I did. It's actually because of something else. How we doing? Okay, maybe. Okay. So let's do a couple problems. I want to show you what they're actually going to look like here in the homework. Oh, here's something. So probabilities, of course, are between what? What's the lowest and the highest? 0% and 100%, or 0 and 1 as decimals. Cool. Of course, 100% chance means it's definitely going to happen. You certainly cannot have a 110% chance. That would mean it's so going to happen that it happens over there too. I don't know what that means, right? Okay, so that's pretty basic. What about... there's a question in the homework that's something like, it's either going to snow or not. So what's the probability that it's going to snow? Now think about it. What's probably going to snow today outside?
Zero.
Yeah, well, maybe not 0, to tell you honestly. You never know. Something could strike the earth, will go way off balance, and I've been watching way too many science fiction movies. But I often get, and actually I think that this is my example. I say it's probably going to snow is 50% here, and I put a big question mark. Because the actual question is about parties. What's the probability that the next president will be a Republican? Now, if you're watching any politics at all, you have some kind of informed opinion or subjective probability to put there, but it's not going to be 50%. It's not 50-50 just because, well, for one thing, we don't just have 2 parties. We have 53 that I know of parties. Did you know that? It's insane. The Whig Party is still out there. Y'all probably know the Green Party, right? Ralph Nader and all that kind of stuff.
Do they still wear wigs?
I don't know.
It'd be ironic if it didn't.
Infiltrate their meeting and tell me, and you'll come back with like powder in your head. They do wear wigs, and I like it. So that doesn't make any sense. Now, what was the problem with this? Why did somebody get that wrong? What was they were obviously thinking that there's what? Why would somebody say 50% chance?
There's doubt.
Either snows or it doesn't.
It's my little brother.
Yes.
Right? My little brother creeping in their head. I'm like, damn, stay out of it. Another example would be, let's say I have chips. This is the really classic probability problem. I have red chips and I have blue chips in a bag. Let's probably pick a red chip. Exactly, I love it. It depends on how many. This is exactly the little box thing I did, the evil little box thing I did. It depends on how many there are in the first place, right? So you can't just say there's red and blue, so it's 50% chance. I have to tell you, what if I told you that there were 6 red and how many, I don't know, 14 blue? What's probably get a red chip? Pick one out of there.
6 out of 20.
Yeah, 6, be careful. 6 out of 20. Can't be 6 out of 14. You gotta always be over the total.
Sorry.
That's all right. Cool. So why is that not 50-50? Because the likelihood of each of these, they're not equal. They're not equally likely. So a situation that would be equally likely, or roughly, we'll consider it equally likely. And actually there's a little bit of a higher chance of having a boy than a girl. Did you know that? It's a little bit of a higher chance, and that's nature trying to help us out, because men die younger on average than women. You guys know that, right? So it's very interesting nature of... You didn't know that? I'm sorry. I just bummed some people out. Doesn't mean you will die earlier if you're a man. It just means on average, men die earlier. And why might that be? Huh? Because some of the jobs we do are more dangerous in general. Now, of course, women are certainly moving into some of those more dangerous jobs, and we're starting to get a little closer to our life expectancy. Say again? Exactly. I was waiting for that. What's the guy say?
I'm fine.
I've had this cold for like 2 months. Go to the hospital. Freaking cold. I'm not going to go to the hospital. Just get a chicken soup. I'm all right. I'm very guilty of that. I don't want to go to the hospital unless I really, really have to, and that's stupid. So yeah, that's another reason men die early. It's because we're stupid. in many ways, makes life more interesting though. Let me see. Oh yeah, that's right. So if I have, I'm going to have 3 kids. What could happen? What could happen if I have 3 kids? Obviously not me, but
Can have all boys.
could have all boys. So I can have boy, boy, boy. Yeah, let's do this. Let's do this a little more systematically, because when we start getting, well, the second one could be a girl. Let's not freak ourselves. So watch this. If we do this, boy, boy, girl. I like it.
Boy, girl, girl.
Boy, girl, boy. Boy, girl, girl. Then you basically repeat those, but you put girls in the front. And that'll capture everything, won't it? You can do that pattern all the time. If you ever took Math 120, you did logic tables. True, true, false, false, true, true. Anybody ever do? No? Yes. You know what I'm talking about. So this maybe looks just familiar. Okay. So then you do girl, boy, boy. Girl, boy, girl. Girl, girl, boy. Girl, girl, girl. Now, assuming, and they are pretty close enough, let's go ahead and say they're equally likely. They are roughly, not quite, but let's just go ahead and say they're 50-50. So each one of these outcomes, these are all outcomes, each one of these, are any of them more likely than the others? No. So when things are all equally likely, probability questions become much easier. What is the probability I have all girls?
1 over 8.
Yeah, 1 out of 8. Very easy question. Whereas over here, now think about this. If I said, what's the probability I get 3 reds if I pick 3 chips out? Nowhere near as easy. You with me? I can make red, 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 blue. I can do the same damn thing I just did there, right? Why wouldn't the probabilities be as easy? Because red and blue are not equally likely. I love it. You with me? So you got to be real careful. We're going to have to come up with a way of doing that kind of problem. We don't have it yet. I can do this kind of problem right now. What's probably have at least one boy?
1 over 8.
7 out of 8. 7 out of 8.
Yeah, you could either be silly and count everything that has a B in it, or just realize I'm only going to leave out the one that doesn't have a B in it, right? So really, another way to do this is 7 out of 8. If you just count 7 with at least one B, right? Another way to do this, though, is anytime you have at least one, and we're talking about stuff you can count. So the least there could be then would be, something I can count, the number of people in here who like lima beans. What's the lowest number that could be? 0, right? Not negative. So I'm trying to make it very specific. The probabilities involving stuff I can count. If I say the probability of at least 1, the only thing that leaves out is none. And opposite probabilities are 1 minus the other one. If the probability is going to rain tomorrow is 20%, what's the probability it's not going to rain? How'd you get that? You did 100% minus 20%, right? 1 minus 0.20 if you want to do decimals. You with me? So how do opposite probabilities relate? One is 1 minus the other one. So it's a really quick way. So it'd be 1 minus, I already did no boys, right? 1/8. So it's still 7/8 either way you look at it. Okay, maybe. Okay. Oh, here we go. If you have your book, look on page 137. I'll put it up here real quick.
you have a meal camera could use?
Say again?
Don't you have a meal camera could use? But they have to plug it underneath a projector. Put it on there.
Oh yeah, I do, but I'm just being lazy. Sort of.
What page? 137.
137, yeah. Did not lie. Okay, cool. So the larger issue here is the idea of false positives, false negatives. So if you go and you have like an HIV test and it comes back positive, you're actually less likely to have it than you feel because you get a decently high amount of false positive results. Are you kind of with me? The only way to really improve the results, the only way you can catch everybody is to basically catch too many people. So you're always going to have some number of false positive test results for something. So this is a polygraph test. So there were, what's one kind of good thing about this polygraph? They lied and they were caught more often than not. Are you with me? So this is the polygraph saying you're lying. So you'd hope that when it said you were lying and you were lying, if this polygraph is good, would be a higher number. And it is. And if you were not lying, it said you weren't lying more often. But if you were not lying, look how many false positives there were. So what's the probability that there's a false positive? And what that really means, another way to say that, is what's the probability that it was a positive test result and you did not lie? So you have to do both things. It had to be a positive test result and you did not lie. So how many times did that happen? 15. I love it. Positive test result, did not lie. You got to love and when you have a chart, it's really just the intersection. What's the intersection between this and this? That. That's the only one that's in both. 15 out of what? Yeah. If I add all these up, what do I get? 57. Careful now. 41, 47, 51. I like it. 98 total people, right? The only time the probability, let me try again. The only time the number in this problem will not be a 98 on the bottom is if I tell you more information. If I don't tell you anything about the person, then how many people could it have been? 98. You with me? I have to tell you something. Oh yeah, it was, they lied. If I said the person you're looking at lied, how many people could it be? 51 people. Then all your probabilities would be over 51 because I told you more information. If I don't tell you a damn thing about them, it's out of 98. So 15 out of 98. So what is that? It's roughly just a little over 15%. 15 point blah, blah, blah percent. All right? You say 15.3. I like it. See? So if there's a 15% chance that if it comes out positive, you were actually not lying. Now, if you get somebody who really believes their polygraph, you're screwed. Well, the machine said you lied. Get out of here. Right? Okay, so let me try this. What's the probability that you got a negative result and they lied? So you lie, but the machine doesn't think you lied. So it's the other way to make a mistake. What's that probability? Yeah, so where would that be? You lied, and the machine didn't think you did. That's 9. Careful, right? So there was a negative result, but you lied. So that's 9. 9 out of 98. Whatever the hell that is. 9.18. Okay, cool. You with it? So if you go in and you're going to lie, what's the chances you're going to get out of there okay?
High.
9%. Yeah, if you lie and the machine lets you off the hook, that happens 9% of the time, at least according to... What kind of probabilities are these, by the way? Are they theoretical, objective, empirical? I love it. Subjective, I say. They're empirical probabilities. These are actual... We'll take them at their word. These are actual cases, right, that happen. So this is empirical probability. Yes, sir?
Like you said, like if you gave more information, it would be like if you said like how many people had a positive result and lied out of the total people who lied, it would be 42 out of 51.
Okay, you're right there with me. Hold on, that's the next place I'm going. You ready? What's the probability that it was a positive test result given that they lied? So I'm giving you information now. This is something called a conditional probability. On the condition that this person lied, what's the probability it was a positive result? So what do we know about this person? What are you given? That they lied. I love it. You're given that they lied. So how many people are we talking about? I like this one, the liars. But how many of them are we talking about? 51. We're talking about these people here, right? We know that given that they lied. So what's my bottom going to be now? What's my denominator? 51. Because it can only be out of those people. Because I know the person lied, so forget the other people, right? So out of the 51 people, how many had positive test results? 42. All right, and that's like 83%. 82.4? See, those conditional probabilities are the ones you really normally want to get. And there's a very classic thing that you guys already know. We talked about it once before, where you use conditional probabilities when you do drug testing. How would conditional probabilities come into play with drug testing? What happens with drug testing? How do you set up a drug test? Some people are... What are you going to do with these people here? They're little. So hopefully this drug is up and grow. I don't know. It's a placebo. You're going to give these guys a placebo, right? See what the brain can do for them. These guys are going to do what? The real stuff. And sometimes you'll have a third group that you just kind of ignore. just live, and we'll see what happens to you, right? Because you want to do that too. What happens normally? Maybe anything you see over here would have happened anyway. So, right? Are you guys kind of with me still? So then conditional probabilities would be, given the person got the placebo, what's the probability that they got better? And you hope that that's lower than, given that they got your new drug, what's the probability that they got better? You with me? So conditional probabilities are used all the damn time. We just don't know that's what they are. So it's when we focus our attention on a subgroup from the sample, given that they were this. So I could have placebo, real drug, nothing, right? I can have that chart set up, and I can ask all these questions. It's later in this class, in Chapter 8, that we'll actually finally be able to test claims. We'll actually be able to take the numbers and see, is it good enough evidence that your drug works better than a sugar pill, right? If the sugar pill works better, hey, just go buy some freaking sugar pills. They're cheaper, right? But no, we'll see. Okay. Blah, 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 blah. Okay, so fourth section, let me just make sure you guys are with me on this. We've actually done a lot of stuff here today, believe it or not. 4.3 is all about OR. What does OR basically mean? What do you do with Jack or 8? What operation is the basic operation you're using? Addition, I love it. So OR basically means add. I say it that way because sometimes you have to also subtract if you count too much, right? So section 4.3 is all about that. They call it the addition rule, which is a little too in your face. It's just what to do with OR. We talked about that one. I want to focus for a little bit on and. Poor little dude, we sort of been shoving to the side a little bit. I want to focus on him directly. And then I'm probably going to let you guys out. I got a 3:30 meeting to get to. Oh, good. Perfect. So section 4.4 and 4.5 actually deal with and, which they're going to call, well, I'm not even going to say it yet. Let me give you my silly example for this. Okay. And actually, I got an even better example. I'm going to show you in the computer in a minute, but this is my silly example that I need no technology for. Let's say you're going to try to get into a fraternity or sorority. You with me? You go to university, you want to get into one of those itties, right? The fraternity, sorority. What happens sometimes that people have actually got in trouble with, my old school actually got in trouble for this. Kids die sometimes horrible. Hazing. Right? And the things you have to go through to actually get into. So let's say that one place isn't so horrible, and all they do is they make you walk down this hallway. And every 5th step I take, somebody slaps me on this cheek. And every 8th step I take, somebody slaps me on that cheek. Right? So if I walk long enough, so that means what? What's the probability I'm going to get slapped on this cheek? How often will I get slapped on this cheek? Do you guys remember what I just said? 1/5 of the time. You with me? 1/5 of the time, I'll get slapped on this cheek, roughly. Now, this is a little more set up than a random probability problem, because I know on the 5th step, I'm going to get slapped. It'd be better if, I'd say just 1/5 of the time I'll get slapped on this cheek, but it's a little easier to see if I set it up like this. So 1/5 of the time I get slapped on that cheek. How often do I get slapped on that cheek? 1/8 of the time. How often will I get slapped on both, this and that? You have the... Say again? 13? So if the probability that the right cheek is 1/5, probably left cheek is 1/8, on what step will I get slapped on both? On the 40th step. Now, at the 40th step, how many times will I have been slapped on both? No? I mean both at once. One time. You with me? So it would be how many times out of 40? 1 out of 40. So what operation did I do to get this and? Multiplication. 5 times 8 is 40. Right? So that's actually exactly, to get this probability of something and something else, I take the probability of the first dude times the probability of the second dude. Most of the time. Sometimes you have to adjust it a little bit. How are we feeling so far? Now let me give you something that's not quite so silly and so contrived. I at least want to get you to realize on one level multiplication makes sense. Now here's something else. I remember living in Florida, we'd go out and watch the space shuttle take off. And back, of course, we've had more accidents than this, but back in '86, the first really big accident with the shuttle, it blew up, right? The teacher on board, all that stuff. Do you guys know what happened? I was there, actually. We normally would go out and watch. For some reason, we didn't. And I was so a geek. I wanted to go to space camp and all that. I was crying that night when I got home I'm starting to cry right now. I'm back in that. I remember sitting in class the first time I heard about it. But what happened was these little thing called O-rings. And they're like valves, basically. They're supposed to keep the fuel going in one direction only. If they go the other direction, the whole thing does what it did. And that morning, it was frosty. It was cold. It was icy. So these things actually ended up failing because they weren't able to do what they're supposed to do. You guys kind of with me? But did they only have one O-ring there? No, they had several. Now, why do you think they would have several there? In case one fails, the other ones are there. It's a fail-safe, right? The worst neighborhood you live in, you have more locks on your door because if they can pick one, you want to make it harder for them. They got to pick the other ones, right? You kind of with me? Okay, cool. So the probability that one O-ring by itself would fail, let's say is, just make it easy, let's say it's, let's make it let's make it 0.01, make it 1%. I was so sick if that was true, but let's just say that. So 1% chance it'll fail by itself, right? You would hope to God if you put another O-ring there, you don't just add them together. That would make no sense. Now there's a 2% chance it'll fail. That doesn't make sense. I put the other one there to make it better. So if I put 100 in there, the thing's definitely going to blow. No, that's not good. You with me? So it can't be just addition. That doesn't make any sense. So the way to look at this is, if 1% of the time that one fails, and I put another one on top of that, so here's this one, here's that one. So if 1% of the time this one fails, what percent of those times would this one also fail? They each fail what percent of the time? 1%. So 1% of these 1% of the times, that one would also fail. You guys kind of with me? It's a lot like that 1/5 and 1/8. 1/8 of the time that I'm here, it'll also slap on that cheek. That's why it's 1/8 of 1/5. 1/8 times 1/5. You with me? Y'all remember that word of means multiply? You ever taught that? A few people have taught that. It sucks. So what would this actually be? 0.01 times 0.01?
Point 0.
Right? Which is 1 out of... So it'd be 0.01 times 0.01, 1, 2, 3, 4. Here, there it is. Should be 1 over 10,000. Yeah, one more point over. Multiply 1, 2, 3, 4. 4 times back. Cool. So when you multiply, what should happen, when you put multiple things in, one more lock, one more O-ring, it should end up making it less likely for something to happen, right? That's the reason. If you really want to get up, you're going to have the final exam, you're like, my alarm might not work. You set another alarm, right? When I'm at a conference, I always do this. I'll set the freaking alarm clock they have, and I'll set my phone alarm, right? Because I'm like, those beds are freaking too comfortable when I'm at a conference. Anyway. So that's the idea with and. Because this would be the probability of the first one fails, O1 fails, and O2. I'm calling O1, one of them, O2, the other one. So far, so good? So, or basically means add, but sometimes you have to subtract off something, right? And basically means multiply, but something. You've got to figure out what that but something is. And that's the last thing we'll do today, is this. Let me make this a little more official. If A and B are independent, one thing happening does not affect the chances of the other thing happening. Right? One O-ring failing doesn't mean the other one's going to have to fail. They both failed because of the icy conditions. It was something else. But they don't affect each other. They're separate things. So if somebody breaks into one lock, will the other lock go, and then unlock? Right? One being done does not affect the chances of the other one. So if they are independent, then the probability of A and B is just the probability of A times the probability of B. Like we did with the slapping on the cheek and the O-rings, we just multiply them straight up. Right? So obviously, what the hell does it mean to not be independent, and what the hell happens then? That's the next question. So let me go back to cards real quick. It might be easier to look at than lie detector tests and all and O-rings. So remind me this. It's probably that I pick a king out of a deck of cards. 452, I like it. 452. 1/13th, right? So now that we understand a little bit about given, which you really want to investigate here, conditional probability is given something else. What's the probability of picking king? Given, it's a club. So how many cards am I talking about now? What do I know about this card? It's a club. So what's the bottom going to be? 13. So the bottom is always dependent on the given. There's 13 clubs, and that's all it could be. Out of those things, how many are kings? Yeah, why didn't you say 4? Because I threw out all the other suits. So there's only one king left that's also a club. The only way it could be on the top there is if you're this and this. So I'm trying to get us to the formula for this. Okay. What about, so that's kind of silly. Did the probability change at all? So what I used to do is I'd pick a card and I'd say, okay, hey, all right, now we're talking. Sorry. So obviously I'm not going to, and I'd say, I'll let you ask one question. You want to put money down on that it's a king. And I'll let you ask one question to see if you should keep your money there or not. And somebody is always like, I'll ask if it's a king. No, if I say no, did that make your situation any better? Just a small bit. Your probability that you're right is just a little bit better or something. Or you got to pick something else, so you're still in the same boat. So if you say, okay, I'll ask you if it's a club. And I say, yes, it's a club. You still have the exact same chance that it's a king. You haven't helped yourself out. You're not any more sure that it's a king. What's a better question to ask?
Is it a king and a club?
No.
Is it a face card?
Is it a face card? I love it. So if you ask, is it a face card? What's probably it's a king given it's a face card? How many face cards? Who knows? I love it. There's 3 face cards, and their face cards are literally the cards of faces. So there's king, queen, jack, 3 for each suit. So there's 12. So the bottom is now going to be 12. Out of those 12 face cards, how many are kings? 4. I haven't lost any kings. They're all still there. So what's my chances now that I'm right? 1 out of 3. I can live with that. That's not bad. Right? If the lottery is 1 out of 3 chance, hell yeah, man, I'm playing that. Instead of 1 out of 7 million or something. So that's the idea with given. That's the only time the bottom is not going to be what it's always supposed to be. Cards, the bottom is supposed to be 52, but if I give you more information, you can throw some cards out. So if I tell you it's a face card, you're only looking at 12 cards, and out of those 12 cards, how many match what you want to be? So can we piece together the general rule that the probability of A given B?
Probability of A divided by probability of B.
So remind me this, why was that a 1 there for the king given club?
There's only 1 king.
Because given that it's a club, the only way it can be a king is if it's a king and a club, right? If I know it's a club, the only way it can be a king also is to be both. So given that it's B, the only way it can be A is if it's both. So on the top goes
P-A.
probably A and B. And the bottom is very straightforward.
B.
I love it. Probability of B. And the reason I can use probabilities is looking back at this one. Real quick, I just want to show you guys. Because you look, these are numbers. These are not probability. 4 of these, 12 of these. But if I look at them as probabilities, what is the probability of a king? 4 out of 52. What's the probability of a face card?
4 out of 12 out of 52.
12 out of 52, right? I should have said king and face card. King and face card was 4 out of 52. What's probably a face card? 12 out of 52. What happens to the over 52s? They cancel out. So you do get 412. So the formula is all about probabilities, ratio of probabilities. But in practice, you could just put the numbers on top and bottom because the denominators are going to cancel out anyway. How do we feel so far? Okay, let's try one problem real quick and then we're going to head out and give you a chart. This is the way I normally like to do. You're always going to get this kind of problem from me on a probability test or quiz. Let's make this very simple. What do you think is a really good first step when I give you a chart of numbers broken out like this? And I want you to find probabilities. What should you do first? Add them all up. I love it. So then you can know what all the denominators are going to be. So there I got it. And I always get, of course I made it, so, okay, good. I always get somebody, for some reason, that adds these and these together and puts that there. What's wrong with doing that? If I add these and these,
Counting them twice.
I've counted everybody twice. I basically got double what I'm supposed to. A real nice thing is these are supposed to add to the same thing. So I got 38 people, and thankfully this is still 38. So don't put 76 there. Right? You don't have 76 people. How are we doing so far? Okay. So let me ask you several questions. What's probably, if I pick one person at random,
138.
I like that. What's the probability that the person is a woman? Probably man or no. Probably a woman and maybe. Probability of no given woman. So try those out real quick. Before I steal those. Thank you for that. Hey. Get a few of those. The last one says no given woman. So make sure everybody's on the right track. What's probably that it's a woman? I like it. So it's going to be over 38. So all these are going to be over 38 except the last one, because that's the one where I give you more information. That's where I can throw some people out. So 38 people out of that, 22 women. And then you can make that into decimal, fraction, percentage, whatever the hell. Right? I have to at least see your fraction work. If you just give me a percentage, I have no idea if there was a mistake made, what it was. So I need to see the ratio you set up, and you can go wherever you want to from there, right? So what would that be as a percentage? Anybody do that? What's that? 57.89? Okay. What about man or no?
19.
Yeah, so or basically means add, but you can't count anybody twice. So if you just go man or no and say 35, what's wrong?
You counted.
How many people did you count twice? You counted 3 people twice. So you could go, okay, 16 plus 19 minus 3. No, just not cards. But even better would just be if you say 16 men, how many no's have you not counted yet?
16.
16. 16 no's that are not men. You haven't counted those yet. So you just don't even add them in the first place. Right? Either way you do it, you get the same thing. 32 out of 38.
It's 19 out of 16. There's 19
Where am I at? That's men or no. Yeah, cool. So it's still, do I know anything about the person? No, I don't. It's just a probability question. I don't know anything about them, so it's going to be out of 38. I like it. So then you can make that into a percentage or whatever you want. What about, so women and maybe. So women and maybe, how many people are both? One. I love it. So and is always restrictive. And will always make things smaller than normal, or will make it bigger. Because or lets more and more things in. So here there's only one person that matches both of these. So it's 1 out of 38. So on this last one, probably of no given woman, what's the bottom going to be? Yeah, why 22? Given it's a woman. So I know I'm dealing with just these people. What I often tell people is just cover the rest of it. That's your whole world. So out of those 22 people, how many said no? 16. There you go. And then you can reduce that, make it a percentage. All right. That's plenty. So I see you guys on Wednesday.